Hello friends, welcome to this session. Today we are going to take a real life problem and formulate it as a binary linear classification problem, right? Just as an example to sort of reiterate what we studied in the earlier session. So let's look at what this example is. Okay, before we get there, a quick summary of the binary linear classifier. The binary linear classifier is basically a special case of the classification problem with just two output classes. And the problem involves finding the best linear decision boundary, indicated in vector notation here, in the space of feature variables such that from the training set, maximum points in one class are on one side and points from the other class are on the other side of this decision boundary, right? There are only two classes. So one set of points in one class are on one side of the decision boundary and the points from the other class are on the other side, and you have to find the best possible linear decision boundary that does that. That's the problem of binary linear classification. And finally, we said that training data in real life has observed variables. These are variables that you gather, right, from your field work. And you may end up having to derive feature variables. You may have to derive feature variables from the observed variables, which may yield better linear separation that you are looking for. Okay, so this was the summary of what you needed to achieve in solving the binary linear classification problem. Okay, so now let's move on to an example. The example I have thought of for you today is the problem of recruitment. So what is the recruitment problem that we are going to talk about today? Okay, this is a real life example. So let's see what it is. Let's say an accounting services firm wants to hire staff. Okay, it receives 5,000 applications in response to an advertisement and has to shortlist approximately 1,000 suitable candidates. Okay, these numbers are not exaggerations. You could easily get, I can talk from my experience. If you put out an advertisement, you can easily get few thousand applications for virtually any position in India. Okay, so a few thousand, 5,000 applications were received by this company, and a short list of 1,000 suitable candidates had to be created. The recruiter or HR of this company normally reviews each application, okay, the 5,000 applications, and shortlists based on certain parameters. Okay, so this is a manual process today where the recruiter or the HR reviews each application and shortlists based on certain parameters. What we want to do is automate the shortlisting process by building a binary linear classifier. Okay, so there are inputs, right? There are two classes, whether a candidate is shortlisted or not shortlisted. So it's a binary classification problem, and what we want to do is basically automate the shortlisting process. We want to automate what is today being done by the recruiters or the HR folks. Okay, so that is the problem that we are going to address. This is a real life problem, like I said, and let's see how we would approach this, how we would formulate this problem. Okay, the first thing, of course, parameters and training data, right? So you go and ask the HR recruiter, what are the parameters he looks at, right? Okay, so you may think, where can I find the HR recruiter of the company? Now, I sort of spent a lot of time looking for the HR recruiter of this imaginary company. I couldn't find him in his office for many days. I was told that he could be found loitering around in the mess or socializing near the coffee machine or the water fountain. So I looked there, didn't find him. Finally, I found him sitting in some random meeting, sitting at the back of the conference room looking at his mobile phone. So I grabbed him after he stepped out. But anyway, so I asked the recruiter, what are the parameters based on which you shortlist your candidates? And the recruiter told me that he looks at academic record, he looks at experience, he looks at salary, looks at joining time, distance to residence, and the number of languages known. So these were some of the parameters based on which the recruiter did his shortlisting. Okay, so the features as per recruiter, okay, as per the recruiter, the features were percentage in BCom, whether the candidate has an MCom degree or not, whether the candidate has an advanced degree or not, number of years of experience, salary expectation, joining period, how long does the candidate take to join once he gets an offer, distance to the workplace, whether the candidate is native, is local, stays close to the office or not, and the number of languages known by the candidate, because sometimes customers have to be explained in different languages. So these are the features as per the recruiter. Okay. Now, the recruiter is also going to give us the training data, but he's not going to hand us the raw data or the raw resumes, right? So this is not, it's not as if he's going to hand us these two stacks of resumes. What we are going to get from the recruiter for training data is a table that looks like this. Okay, so a table whereby for each candidate, candidate 1, candidate 2, candidates are sort of indicated as columns. For each of these candidates, the values of the features are listed. The numerical values of the features are listed. For MCOM, it's just yes or no, but there are the others have numerical values. And finally, because this is training data, the recruiter also tells you whether this particular candidate was shortlisted or not shortlisted, right? So this is the kind of training data that we are going to consider for the purpose of our illustration. So going from raw data, going from files, going from binary files, PDF files to a table like this is a different problem. Okay, so this is like an extraction problem that is not a part of this particular session. The techniques used for extracting data from PDF files and so on and so forth is a matter of study in a separate session. So right now we are not going to think of this. Okay, so we are not going to think of this. We are only going to think of a table that looks like this. Okay, great. So the recruiter has told us the features that he looks for, and the recruiter has also told us, has given us some training data. Training data maybe for 1,000 candidates of or whatever training data he had, let's say based on his prior experience, could have, let's say, 2,500 training points, right? So this is what we got. Assumptions. Okay. Now this is a very important slide, very important slide. Now, we did not discuss this in the earlier lecture for a reason, but the binary linear classifier makes certain assumptions about the feature variables used. Okay. And these assumptions are as follows. So linearity. Linearity basically means that the impact on the result of any one feature variable is linear. Okay. So each feature variable, its value has a linear impact on the result. This is the first assumption. Independent variables. Independent variables means that the feature variables that you take are not statistically correlated. They are statistically independent. Statistically independent. That is what this assumption says. Homozydasticity. Okay. What this is, this says that if you make an error in a feature variable, the resulting error in the output remains the same irrespective of the value of that feature variable. Okay, I will repeat. The error you make in the feature variable, okay, you could make an error in recording a feature variable. The resulting error in the output due to that error in that feature variable does not change depending upon where in the scale of the feature variable value you are. Okay, so that is homoscedasticity. And finally, normality. Normality relates to the probability distribution, which is assumed to be normal. You know what a normal distribution is based on your probability course. So it assumes a probability distribution, it assumes a normal probability distribution for the feature variables. Okay, so these are assumptions. Now I want to make a very, very important point. Okay, hereafter we will not use the word assumptions in our work. Okay, so we will erase this word from our vocabulary, and I'll tell you why. Okay, the word assumption seems to indicate that it is not your business to ensure these things. Okay, it sort of seems to suggest that these are assumptions that you assume are true, and you merrily continue to sort of scribble away your code or your algorithms or whatever, right? But that is not how it works in practical life. These are not assumptions. These should actually be called pre-work, because ensuring these things is your responsibility. Remember, we said in the last lecture that creating ideal feature variables from the observed variables is your responsibility in a way that ensures good linear separation. That was your responsibility. So these things, right? These things should be called pre-work, and they should not be called assumptions. We will not call them assumptions. We will do the best we can. Okay, we will do the best we can to ensure that this is done, that this is true about the feature variables that we choose in our examples or in the problems that we want to solve at work. Okay, so pre-work, let's call them pre-work. Okay, so let's go from the observed variables to the feature variables. The earlier table showed you the observed variables, and we are going to transition to the feature variables. This is one example of doing that. It's a simplistic way of doing that, but I'm trying to do this just to indicate that this step should be a part of your problem solution. Okay, so what am I going to do over here? Just as a as a simplistic approach, there is percentage in BCom, right? That was one of the variables, observed variables, and MCom was yes or no. I'm just going to allocate a +5 for all candidates who have an MCom degree and add it to the percentage of BCom. Okay, so this becomes my feature variable based on these two observed variables. Okay. Now, years of experience. Instead of years of experience, I am going to start using log of years of experience. And why am I doing that? Because any recruiter will tell you that as the number of years increases, the importance of the years of experience sort of goes down. Okay, so the curve kind of may look something like this. I mean, may not exactly be a log, but something like this. So it makes a big difference if a guy has 2 years of experience versus 4 years of experience. But it doesn't make all that much of a difference if the guy has 22 years of experience versus 24 years of experience, right? That's the point I'm trying to make. And therefore, we will use log of the years of experience. Okay. Sort of an attempt to linearize. Okay, I'm giving you these examples to show you how I'm trying to linearize the input variables, right? Here I sort of combine two variables and reduce the dependency. Let's look at the next one. Here our next observed variable was salary expectation. And now you know that mostly salary is correlated, is statistically correlated with the years of experience, right? Because more the salary, more the years of experience, more the salary, right? So instead of using salary as as a variable, I'm going to use salary divided by years of experience. Okay, so the expectation, it's true to a large extent. The expectation is that the ratio of the salary to years of experience is not statistically related to either the salary or the years of experience, right? Because it's a ratio of the two. And what you want to do is sort of take people for whom this ratio is as less as possible. So again, an attempt to sort of make this variable statistically independent. Joining period. In the case of joining period, it could be the reverse of the years of experience. So if somebody has 2 months of joining period versus 3 months, that's a huge difference. If it is just 5 days versus 10 days, it's not a big difference. So I'm looking at a curve that looks like this, right? Of the impact of joining period, and I'm just going to sort of treat this as a square, and I'm going to consider the feature variable as joining period to the power 2. Okay. Distance to workplace, let's just keep it as is. Okay. And number of languages also, let's just keep as is. So this is an attempt here to show you how you can make some efforts to linearize the feature variables. You can try to make them independent and so on and so forth. Okay, so this is the kind of pre-work that you may have to do on real life examples. Later on in subsequent lectures, we will also look at formally how this can be done and so on and so forth. There are some techniques to do it. That will be a part of subsequent sessions. But here I want to stress the fact that there is some pre-work to be done to make the feature variables independent, uncorrelated, and so on and so forth. Okay, so consider the problem here. I always keep going back to examples. This is a 3D view, but your training data has basically 6 feature variables, right? So there are 6 of these now. There were 7 observed variables. There are 6 feature variables, right? So this is a 6-dimensional space. Okay, 6-dimensional space, and in this 6-dimensional space, these points represent candidates who were selected and rejected. So let's say the yellow dots were candidates who were rejected and the blue dots were candidates who were selected, right? And what you have to do here is, of course, I keep repeating this over and over, find this best plane that gives you a separation between the blue dots and the yellow dots. Okay. Formally, what do we need to do? This is the equation of a hyperplane in 6 dimensions, right? W1, x1, W2, x2 going to W6, x6 plus the constant equal to 0. This is the equation of the hyperplane in 6 dimensions, right? And this hyperplane is defined by these weights W1, W2, W6, W0. And we have to find the values of these. We have to find the values of these coefficients such that it gives you the best possible division of the 2 classes in the training samples. Okay. This we saw last time. How do we do this? How do we solve problems like these? Okay. Problems like these are solved iteratively. Okay, iteratively via a process called optimization. Okay, so it's not as if you get the answer to these problems in a closed form. You solve some equations and you get W1 equal to a value, W2 equal to value, and so on. That's not how it works. The solution is arrived at iteratively. Okay, iteratively. This is an example of what is known as an optimization problem. Okay, so optimization means making something better and better and better. And iteratively means that you do it in steps, one after another, successively try to do better and better and better. So these problems fall in the category of optimization problems, which are typically solved iteratively. Okay. So let me kind of give you a feel for what this optimization is going to do. I'm going to formalize this in the subsequent lecture mathematically. Okay. But let me give you a gut feel for what this thing is going to do. Okay, so this was your training data, and now as you can see, you no longer have the observed variables, but you have the feature variables, and for each candidate these feature variables have some value. Okay, so for each candidate this vector is called the feature vector for candidate 1, feature vector for candidate 2, and so on and so forth. Okay, feature vector for candidate 2 and so on and so forth. So these are the feature vectors for the candidates, and for each candidate in the training set there is also a result, either pass or a fail, because this is a binary classification problem. Okay, now you have these weights. W1 is associated with x1, W2 is associated. So let's say that this is x1, x2, and so on and so forth, right? These are going all the way down to x6, right? Sorry, my x doesn't. Okay. So W1, x1, W2, x2, W3, x3, and W0 is a constant. What we are going to do is calculate this, right? So we have to calculate this. This is what has to be calculated. This is what has to be calculated for each of these candidates, right? With these W values that you have begun with. Okay. So you began with these W values. Okay. You began with these W values, and you have to, sorry, this is X1, X2, X6, right? So W1, X1 for candidate 1, right? So for candidate 1, W1, X1 would be 0.2 multiplied by 65 plus W2, X2 would be 13.6 multiplied by 0.5, so on and so forth, to 5 multiplied by 1 plus 2.3, right? So similarly for candidate 2, you would do 0.2 multiplied by 48 and so on and so forth, right? So you do these for all candidates and get the results, right? So you get the results. This will evaluate to something, this will evaluate to something, and so on and so forth. Okay. Now, what you need, your ideal scenario is the situation where for all the candidates who had passed, what this evaluates to is either positive or negative, and for fail it's the other one. So for example, you would love it if for all the candidates who passed, this value was positive and this value was negative for all candidates who failed, or vice versa, right? So either could be plus or minus, but all pass have to be on one side and all fail have to be on the other side. That's your dream situation. That's what you strive to do. Now this may not happen. You may observe that, you know, these values of W don't quite work. Okay, these values of W don't quite work, and therefore this hyperplane is not a good separator. What do? You modify the values of W. So for example, you may change W0 to something 2.1, so on and so forth. Instead of this, you may have W1 0.7, whatever. You change the values. Of W's and do the exercise once again. Do this computation for each candidate and see if all the pass are on have one sign and all the fails have the other sign. Okay, that's what you do. If that doesn't work for you, you change the values of W again and keep iterating, right? That's how this iteration process works. Now, the topic of our next session is going to be how we do this in a scientific way, right? You cannot randomly be changing the values of W, because then you would never end up with a good solution. So there has to be a method to that madness. There has to be a mechanism in which you change the values of W. There has to be a mechanism in which the values of W are changed in a manner where you sort of keep getting better and better and better. Right? That is exactly what the process of optimization does, and that is why it's called iterative, because the values of W keep changing. Okay, so I have given you a gut feel for what that optimization process is going to do, and we are going to formalize this. We are going to formalize this mathematically in our next lecture. This is exactly what iterative optimization was. So what iterative optimization is for our problem is that for a set of values of the W's, you find the performance. Okay. So I'm using a colloquial English term performance to basically refer to how well the pass and the fails did in terms of all pass having one sign and all fails having the other sign, right? So we have to define a metric for that, but I'm using the word performance in sort of a loose colloquial way, right? You find the performance, then you modify the values of W's, in a manner expected to improve that performance. Okay, so you change the values of W so that your performance improves, right? And you keep repeating, you keep iterating, or you keep repeating till further improvement is not possible. Okay, till further improvement is not possible. This is what iterative optimization is going to do. Now, in the earlier lecture and this one, we've sort of spoken colloquially about performance and, set, iterate, etc., etc. But next lecture is going to focus specifically on these facts. So we will define what performance is. Okay, we will mathematically come up with what performance could mean in our case. Okay, and we will also talk about how you modify the values of W, to enhance that performance. Okay, so these two English words in this session are going to be formalized into mathematical equations in our subsequent session. But the idea, the gut feel remains the same, right? You keep iterating, you keep modifying, you keep monitoring the performance and try to get better. Summary. This is a short one. Summary. We discussed a real life example of resume shortlisting. Okay, I came up with this example because I thought it had interesting variables that you could play around with and so on and so forth. I hope you liked the example that I gave. I hope it was useful in conveying what the binary linear classifier seeks to achieve, right? So we discussed the real life example of resume shortlisting. Then we set up the problem with modified feature variables. Very important step for a practicing engineer, though you may not see this step in too many online courses or lectures and so on and so forth. But very important step for a practicing engineer. And finally, we set the broad expectation of what the iterative solution is supposed to do. Okay, so that is what we did in this lecture. Next lecture, as you would anticipate, is going to be a little bit more mathematical because we are going to formalize all the hand waving we have done so far in terms of optimization. Great. I'll see you next time.